to the Cypher query language. So for this, I'm gonna use the Enricher KG Neo4j database so that we have like something more interesting to play around. But you can definitely change this up with like the example database that we've ingested if you're playing around with like the knowledge graph demo one. But here's how it looks like. So as I mentioned, Cypher query language, this is the language that is being used to query Neo4j. And the good thing about Cypher is that it's actually really intuitive on how it works. So the idea is all nodes are represented by parentheses and all edges are represented by square brackets. So here, um, everything after like if you have like a colon and then like a type, so that means that you're looking for like the specific node type. And then here, this is like a filter for like a property. So maybe you're filtering like label. So I want the label named GFAP. Here is like the relationship filter. So we're looking for a relationship called for KEG 2021 human. And then here we're just assigning everything that is connected with GFAP via KEG 2021 human to this variable P, and you return that variable. And then the limit is 25. So let's actually try running this one. Let's see. You run that one. Oops. Hmm. Maybe I have like the wrong name. I think it's not KEG 2021 human. Actually, it's KEG pathway. Okay. Okay, maybe there's no GFAP on KEG pathway, or maybe I did something wrong. Let's try this. Hmm. Maybe there's no GFAP for like that one, but let's try other gene ACE2. Hmm. Wait a minute. There you go. Like it's the directionality that's messing it up. But let's try it again. There you go. So it just returns you like a pathway that is connected with like GFAT because you're just returning the P variable here, wherein we just want to return like the node that is connected with GFAT. But this one just jacks that signaling. We'll go to the more examples in a bit, but that's just like an example. Um, and next, so here are just nodes. Um, in Cypher, um, so as I mentioned, everything in parentheses refers to any nodes in the knowledge graph. So if it has a colon and the node type, so this refers to like a gene nodes, but it is not really assigned to a specific variable. And then A, if you have like a variable before like a colon, you actually assign that gene to like that variable. And then if you have like this one, we're actually looking for drugs with label dexamethasone and assign it to like the variable A. Next, we have queries. As I mentioned, this can be directed or undirected. And if depending on your query, if it can return you none if it is really directed. But it can actually be agnostic if you just remove the arrows. So if you remove the arrows, something like this, it will give you like it will, it can be agnostic with like the direction. So this one, so um a dash square bracket dash B refers to any relationship between two nodes in the knowledge graph. Actually, if you're doing this, you can actually even omit the square bracket because it just means if it's dash dash dash, that means you're looking for like a relationship, any relationship. But if you want to define a relationship, you don't just put here, example, this KEG 2021 human or KEG pathway for like that example. So it returns connections where the node A is connected to node B via KEG 2021. And here you just do like variable assignments. If you put C in here, and then A's some relation. So if you have like some, I mentioned something, if you have like scores like the gene expression earlier from the links example, you can also filter like the edges based on like these kinds of filters. And yeah, let's do the demo now. So the knowledge graph demo also has this Cypher library, Cypher notebook. So as I mentioned, unlike relational databases, so graph databases do not really have uniform query language. So platforms typically build their own query language, but Cypher, originally built for Neo4j, was is currently being opened up using this Open Cypher project. So as I mentioned, you can go to localhost 7474 once you have your Neo4j console up, but you can also use this notebook. So this uses Py2Neo, which I mentioned that Neo4j has several libraries. So this is like the library it uses for Python and PyCytoscript to generate graph visualization in this Jupyter notebook. Let's just import all the libraries. Oh, before anything else, also um you need to do also cp on .env dot example dot env. So what you're doing is you're just copying your environment variables from the example to .env. So that should work. So you don't have to modify anything. But yeah, so we're going to load our environment variables. So we're just going to load Neo4j URL, Neo4j user, and Neo4j password and load that in the graph. So that way we are now connected to our database. So let's now try doing Cypher clear function. Let's um just run this thing. So these are just stuff that we need to do to run our Cypher query. So you don't have to worry about that. I've formatted it for you. Um, but yeah, so this is how a Cypher query looks like. So querying nodes. So if we have like this Cypher query, so match a drug label afatinib, so return A. So the match keyword here. So queries for nodes, relationships, or path that matching the succeeding relationship. So for this one, it's just matching a node. So queries wrapped in parentheses are matched on nodes. And in this case, we want drug nodes with the label afatinib. And then A, the preceding A in the filter is the variable wherein we want to store the results. And this is what we actually return. So now let's try some examples. So consider this one wherein we're not really filtering for anything. So we just want any 5 nodes. So that's A limit 5. So we return something that looks like this. And it will just returns to you like 5 nodes from the database. And if you want to get 5 nodes from the Go biological process, you can do something that looks like this. So you just filter for like that node type and you get something that looks like, let me just put this down. Looks like this. So and finally, if you want to, do the afatinib example, so it's kind of different for like the enricher KG example database. So you want to look at links L1000 Kempert consensus signatures with the label afatinib, and then return a. So it just returns you like that node with the label afatinib. So you can also do something. So I mean, if you want to, you can also do something like this. So if you do, you can also Neo4j also has like this where clause. So if you do where a dot label equals afatinib, afatinib, yeah, I think something like that. And it will also return you something like, if you don't know, if you don't know the the type of the node. The advantage of this is, since the nodes are indexed, it will actually use the index to make the query faster. But if you don't know like what the name of the node is, you can also use like this where clauses so that you can further filter your queries. So one thing is that without any filter, our graph database will match any type of nodes and then return it. So it's really important that we have set up these limits. For this one, you don't really need the limit because you're just returning one node. But for this one, like for this example, and also this example, because imagine this, if you do match A, return A, it will return you all of the nodes in that library, and it will be really big, and it will probably crash your database if, or crash your computer if you don't have like enough memory to handle it. So it's important that we have limits so that we won't get overwhelmed with the results also. Next, relationships. So let's dissect. So here are how to query relations. So we just do match. Again, all relations are queried using square brackets, and the query wrap in the square bracket matches a relationship. In this case, go BP. So and then we have directionality based on the arrows, or if we want to be agnostic, we just remove the arrows. So here we look at KEGG pathway. Um, and then so we get like all of the relationship, all like 10 nodes that are connected via KEGG pathway. And here you return like ABC transporters, and here are like the connections with it. So now let's try like a more interesting use case, like how do we query for neighbors? So this is basically the single term search for enriched KG we have earlier. So this finds the immediate neighbors of a gene. So if you run match a gene label ACE2, so it just returns to you all of the, well, not all, like the 10 connections, or let's make this 5 maybe, of ACE2. So if you run that, it just returns to you, since you did not like specify any relationship, it will return to you like the first 5 connections of ACE2. So I guess like as a checkpoint exercise, if you want to return a query that returns 10 terms that are connected with the gene CLOFA, you have something that looks like this. So match gene, label KL, and then you just return the path. And if you run that, you have something that looks like this. So since we did not like put any label on the relationship, so it just returns any like first 10, or however the Neo4j prioritize the database. So let's try a more interesting one. So how about looking at the KEGG pathway for the gene KL? So I guess we can answer that. So from here, we can fine tune that query. If you do something like this, so KEGG pathway, you do something like that, and you enter it, it will return to you all of, well, not all, like at least 10. For this one, it only has 5 KEGG terms that are connected with the gene KL, and it will return you this one. So so this is for the immediate neighbors, like the single term search. Now, what if we want to query longer paths? Suppose you have want to discover a path of length 2 that connects gene map K1 to the gene CRKL. So there are several ways of doing this. You can create like this path in itself. So, you can have gene is connected with like whatever term, and then you can it's connected to like this gene CRKL. So if you run this, well, I should have not run it, but it's not that slow. Here you go. So it actually like just looks at the terms that are overlapping between CRKL and MapK1. Additionally, we can also use this variable length pattern matching. So if instead of doing this query, we can actually just say, oh, I just want it to be of length 2, which is the asterisk 2. So if you do that, you don't have to like define all that the complex path. It will just return you like path of length 2. So if you run that, you have something that looks like this. But do note that there is some differences between the results of these two. It's not like, um, because it's in a way of how like the algorithm prioritizes paths between like these two choices. So there's some differences with how the algorithm prioritize paths on this one and this one. That's why there's a difference. But basically we're just doing the similar things. If you remove the limit here, it will return you the same answer. And one thing about this approach is that we can actually have like this variable patterns. So if you want, oh, not I don't only want a path of length 2, I want it from path length 2 to path length 4. So I can define something like this. So asterisk 2 dot dot 4, that means, like a minimum of 2 and then a maximum of 4. And it will return you that the paths that contains that one. So the 10, limit 10. So no, it will return you like the matches with that kind of query. So this is how it looks like right right now. Um yeah. So checkpoint exercise. So how about we want to find at least 10 shared genes between the Go biological process, apoptotic process 006915, and KEGG 2021 human apoptosis. So easy. I mean, I can do it. We can do it something like this. Match a Go biological process 2021 label is apoptotic process, and then you can do star 2, and then KEGG 2021 human label is apoptosis. I maybe do P equals and then return P, maybe limit 10. Let's try if this works. Hmm. Anyway, while that is running, oh, actually, this is another example of how to do it. We can also use all shortest paths. So another option is to actually use this one, and this is actually a little bit easier because it returns all of the shortest paths between like these two nodes. So for example, we have this thing that we have earlier. Yeah, maybe this is the thing about like the variable functionality is like it's kind of slow. So let's just stop that one. Oh, it worked. Okay. It finished. So this is how it looks like. But another option is to actually use the all shortest paths. So it also does something like that, and it returns like the shortest path between apoptosis and apoptotic process. So you just put it here like this. You have like this function, put the query inside, and if you run this, it should return you. It's much faster than what we had earlier, but it will return to you like this result. So which is kind of faster. And yeah, with that, the Cypher, and if you have like want to know more about Cypher, you can just check this out. Like we have like some resources here, and we have also like this resources for Cypher querying. And okay, so